Okay, you should be good to go now. So have a good session.
Okay, great, thanks.
All right, so we are very happy to have Stefan Dziembowski as our second invited speaker of CHESS 2020. So Stefan is a professor at the University of Warsaw, which he joined now as head of the cryptography and data security group after a PhD from Aarhus, Denmark, and some postdocs at ETH and PISA and University of Rome. He's very much on the side of the theoretical side of cryptography. So he was previously program chair for TCC 2018. He's going to be the next co-chair of Eurocrypt next year. So he has also worked on several topics that are very relevant to the chess community, and particularly the question of modeling leakage, for example. So he's the author of very well-known papers in this community about the noisy leakage model, for example, and how it relates to the probing model. So these are questions that are critical for what little we have of theoretical understanding of side-channel security. So therefore, we are very happy to have him. And Stefan, the floor is yours.
Thank you very much. Thank you, Magdi, for the introduction, and thank you for inviting me here. I'm going to talk about the theory of leakage. And I have a couple of slides at the beginning, like introductory slides to leakage. I'm going to show them very quickly because I'm assuming that for this audience, I don't really have to give much introduction on this topic. So, wait, how do I change? Yes. Okay, so side channel leakage, I guess you all know it. It's a very powerful technique for attacking cryptographic hardware introduced to the academic community by Paul Kocher in the 90s. And basically, it's based on the assumption that many cryptographic devices can be broken by attacking the hardware instead of attacking the algorithms. And you can attack it in many different ways, like measuring power consumption or some electromagnetic radiation and so on. And since the publication of Kocher in the 90s, there were tons of papers on this topic, especially at this conference. And the main motivation behind this paper is always the same, that well, traditional black box modeling of cryptography is too weak. So by black box modeling, I mean traditional modeling, like how you start teaching crypto, is there is an adversary, there is a device, right? And the adversary interacts with the device via input and output. That's called the black box access. So it can happen that this is secure, while in real life, when you really implement it on some concrete device, then it becomes insecure precisely because the adversary gets the leakage. Okay? So this is the general motivation behind all this research, to make things secure even if there is some leakage happening. So in my view, what is the role of theory here? So first of all, so we are here to help, right? We try to interact with this community, practitioners community, and I think the main topics in which we can help are proposing new tools, using or inspired by some previously known tools in theory, studying models of leakage, and showing security proofs. And I'm going to give you some examples of theory success in all these three aspects. Let me also say that the pioneering papers on this topic were by, I mean, I guess usually the following two papers are mentioned: Ishai et al. From Crypto and Mikali and Raisin from TCC around 20 years ago. I'm going to talk more about Ishai, Sahar, and Wagnerson. Okay, so one way to look at this is leakage resilience is a very important and challenging area. It's extremely complicated, and theory is one of its tools. Okay, I think it's important to say that it's not like the tool. We are aware of this working in theory. That is just one of the tools, and actually, I would even say that theory is neither sufficient nor necessary in this area. at least strictly speaking, because, for example, security theorems are only as meaningful as the model behind them. So you can have beautiful theoretical results that don't have that much impact in practice, and doesn't make sense to implement something in real life just because it has a theory proof. You should do more work on analyzing security than just doing the proof. And it's also not necessary, strictly speaking, because you can show many successful constructions that are secure and came without any security proof. This is not true for all areas of crypto. I think if you talk about cryptographic protocols, for example, then usually people would say nowadays that proofs are absolutely crucial. It's not true, I think, for hardware, cryptographic hardware. Yet, I think theory can help. And I will give you some examples. For example, just to start with something, theorems can simplify complex security analysis, for example. So what is a typical ingredient of every leakage theory paper? There is something there called leakage model. I mean, usually in practical papers, there is also something like this, but somehow theory papers are very careful about specifying this. So by leakage model, we typically mean, well, there is the adversary, there is a device, right? And so what do we have to model here? There has to be a formal mathematical model of the device. So say a Boolean circuit or something like this. There is a description of what can leak. So basically description of this leakage, mathematical description, and description of what is the goal of the adversary. These are like the three main ingredients. What is the goal of this talk? As I said, I will give you some examples of how theory contributed here. And I should also give some disclaimers. So first of all, many things will be simplified. Okay, I will give you pointers to the literature to read more. There are several important results that I'm going not to talk about because of the lack of time. I apologize if I don't cover some very important results. Especially, I'm not going to talk much about leakage resilient public key crypto, which is a very important part of leakage resilient theory, but I don't have time to cover this. And the order is not chronological, so I'm going to more like go by topic, not by time. Okay, and this is the outline of today's talk. I will first talk about probing model, which I guess many of you know, but I think probably not all. So I'm just going to start with this, and then I will talk about other models, reductions between models, and then I will have some conclusion at the end. Okay, so probing model. This was formalized in probably one of the first theory papers on leakage, which is the paper that I already mentioned, Ishai, Saha, and Wagner, Crypto 2003. And what they construct there is a general compiler. So it's like a general construction, not specific for any concrete cryptographic scheme, but a general construction that is secure in the probing model that they introduce there. And I'm going to tell you in a moment what probing model is. As I said, you need to specify these three things, right? So you need to specify how the device is modeled, what can leak, and what is the goal of the adversary. Okay. So we'll start with this, and we'll say what is this, and then what is this. So the model of the device is very simple. It's a Boolean circuit. So this is a Boolean circuit. I guess I don't have to say much about this. It has what gates and wires, right? Wires carry values from Z2, so bits 0, 1. Without loss of generality, you can assume that the gates are just XOR and conjunction, plus and times, right? The circuit has input and output, and since we want to model continuous computation divided into rounds, we'll also have a state memory, which will be used as follows. So it starts with some initial state, then the circuit is evaluated, some output is produced, and then this old states get replaced with the new state. Okay? So it's quite a simple model. You can think of a state as a cryptographic key or something like this. Okay? So it can even stay the same, for example, but can also evolve. The adversary can probe at most W wires. This is called W limited probing, and by probing I mean the following. So, okay, so this is the adversary. So in all these leakage models, the adversary still has power to do what he can do without leakage, right? So he can produce some input, feed it to the device, and then he can choose up to W wires in each round and learn the values here. Okay? The remaining wires remain hidden from him. And then the computation happens. He learns the value of these wires, and then he gets the output. Okay? And he can play like this with the device. Informally speaking, the goal of the adversary is to learn the states, but of course, formally it's formalized in a different way. But you can think of it also like this for the purpose of like informal definition. I hope it's clear. Yes, and there was this real-life metafor in the paper that it corresponds to the adversary inserting needles into the device. Okay? So the adversary has some needles, like 4 needles in this case. He can put them into the device and read off the values on the wires. And of course, this sparks an obvious criticism because what the practitioners would tell you is that in real life, leakage looks more like this. Okay? It's not like that you insert wires. It's more like you measure some current or some electromagnetic radiation, and you get a graph. Okay? So obviously, there is a good question if it's realistic or not. So let's address it first. Okay, so first of all, it's just a starting point. Okay, so and even the authors of ISW say it explicitly that it's initial study, and they even say this would be interesting to extend the results to cover wider class of realistic attacks. Okay, so nobody here claims that it's like immediately practical. Then, of course, secure in some model doesn't mean that it's automatically not secure in other models. So you can say, okay, at least it's secure in the probing model. And finally, maybe other models, more complex models, could be in fact reduced to this model. And I'm going to tell you more about the reductions between models later. Okay, so I'm going to tell you now a little bit about how ISW works, because I think it's instructive to see it. So it starts with the initial question, how to store a secret on a leaky device. So on a device where the adversary can probe some bits. So of course, if you just store a value as it is on a device, and the adversary can probe the device, then he can always directly probe the wires that have this value. So there are like 3 values that you want to hide, S, T, and U. Then the adversary can just probe the wires that go out of the cells, and he will learn the value. Okay? So obviously, storing just secrets in plaintext on the device that can be attacked with probing, that's not such a great idea. So the idea that is quite natural is to encode, instead of storing directly, encode the secret. And well, the simplest encoding we know is M out of M secret sharing with M equal to W plus 1. So W is the number of probes that the adversary can make. So this would look like this. So encode of S would be S1 up to SM, such that all these S's are random, but they sum to S. Okay? So this is like a very simple M out of M secret sharing. To decode, you just compute the sum. This all happens modulo 2, of course. And that was known before ISW, actually. It was proposed, at least in 2 papers, in Goubin and Patarin at CHES in 99, and the same year, Chari et al. And so that was like a very, very nice idea prior to the work of ISW. By the way, it's also called masking, this encoding, often in the practical literature. Okay, so how to do it for a circuit? There is an obvious way to do it. Well, at least obvious point to start. Instead of, well, I mean, just take this thing like encoding of values and do it for every wire, right? So you would have, like here, have an original circuit. You would do like this. So in this case, W is equal to 2 and M is equal to 3. You would just, so this should be secure against probing of 2 wires. And yeah, this is called a wire bundle sometimes, like group of wires corresponding to 1 wire in the original circuit. And then, of course, like you look at it, it looks nice, but then there's an obvious question, which is how to compute on the wire bundles. Okay, so you have some wires here, and then how to compute in such a way that what you get here actually is the encoding of the inputs. Okay? So this is a very natural question, and actually it has a simple answer in one case, namely in the case of addition or XOR. Right? Why? Because the encode function is linear. So basically we have this property that if we encode S and T and then decode and we sum up these two vectors as vectors, then if we later decode to get the sum of the encoded values, right? And that was also known before ISW. That's, I think, from the paper of Gube and Pataran, chess 99. So just if you look at the circuit, that would look like this, right? That you have here you have S in the original circuit before compilation, you have S, T, and they have to produce U. And say this S is encoded as S1, S2, S3, and the same with T's. Then in the transformed circuit, you would just transform it like this, that to produce the encoding of U, you would sum up S1 and you would to produce U1, you would sum up S1 and T1, then U2, S2, and T2, and so on, right? And this is the encoding of U, precisely because of the linearity. Okay. And the main contribution of ISW is how to handle multiplication in this case. Okay? So how to handle multiplication? So let's look at the multiplication. Well, and let's look at the most naive approach, like how to multiply. Okay? So how to multiply? You have encoding of say S and encoding of T again, and you multiply like this, right? So you could multiply simply each pair of elements, and then get each term like this, right? And then you sum everything. Okay, so this is like a traditional way you would multiply. And of course, you don't want to sum things on the chip, because then you would again get like a single value is unprotected, unmasked. So you have to do it in some other way. So let's look at the situation. So we have the following. We have this S and T, right? S and T is are these two values, S and T. So we have a product of S and T that looks like, and we have encoding that looks like this of the product. But it has a problem. So it's not uniformly random, right? Because it came as a product of two encodings. So it's easy to see that it's not like a uniformly random encoding. And, which is even worse, it's too long. So it has a length m square, while we want encodings of length m. Okay? So maybe it's not a problem if you do it once, but if you do it multiple times, it definitely becomes a problem, because it really blows up the whole circuit. Okay? So you have the situation how to handle this. There is no time for me to tell you the details. You should check the original paper in case you haven't seen it yet. So they have some way to do it. The transformation that uses fresh randomness and is secure even if some wire leaks. Okay, leak. So you don't want to assume that there is no leakage here, right? Because then it would be trivial to do. You want to say that, okay, even this procedure of reducing these encodings leaks. So what happens here is you start with an encoding that is too long and non-random, and you do some strange things, and then you get shorter encoding that encodes the same value. Okay, so you kind of reduce the long and non-random encoding to shorter and random using some fresh randomness. And you do it in a secure way. Okay? It's not such a complicated scheme, but I don't have time to show it now. So what's important again is that you had m square non-uniform values and you arrive with m uniform values after this transformation. Okay, and actually the name for this that they have, or at least one of the names that they have in the paper is MPC on silicon. So let me tell you why they call it MPC on silicon. And the reason for this is that actually it feels very similar to something that was done since the 80s in the area called secure multi-party computation protocols. It's usually abbreviated as MPC. Okay? So this is, it's not really exactly the same, but it looks very similar. And I will tell you on the next slide why. So this area was started by theoreticians in the 80s, and it had many envisioned applications like auctions, voting, cloud computing. These are all these protocols where a number of parties on the internet want to do something together without revealing their secrets. Okay? And that didn't look like it had anything to do with secure hardware. Okay? So it's like completely different technological applications. But nobody imagined that this will be used for secure hardware until ISW that actually used something very similar for this purpose. So there's not time for me really to show you how it works in detail, but basically the key point is that if you look at MPCs, then they also have this problem. So what they do there is they share their secrets using polynomials. Okay? So they also have a situation at some point that they have some points on a random polynomial of degree 2n, that evaluates to something and 0.0, so this is like shamming secret sharing. And then they have a special protocol for like that also uses secure transformation and fresh randomness and arrives to fresh values, this U1 to UM, that also are points on the polynomial that are evaluated to the same. Okay, so there's this big similarity here. So we are also starting with non-random, we get random, and we reduced something. Okay, in this case, we reduced the degree of the polynomial from to n to n. This is very kind of hand wavy high level what I'm saying, but basically the bottom line here is it's not really exactly the same technique as used in MPCs because the protocol is slightly different, but the spirit is very similar, and it clearly was clearly inspired by the ideas used in MPCs. Okay, so that was ISW. Let me tell you quickly what was the impact. So there was this very important paper by Riven and Proof at CHESS 2010 when they had the observation that this compiler also works over arbitrary fields, not only over Z2. So you just take the same as before, but wires will carry values from a field F, right? And that was very important because AES is built using a finite field, right? So then you could use this to mask AES. So it was a very nice observation. And then lots of papers. This paper has a lot of citations from the practical community, even very recently. You can try to optimize different aspects there. There are people who are trying even to use automated tools to optimize some things there. So in general, it was a very fruitful area, and it is. I'm not sure to which extent it's used in practice right now, but I think to a certain extent, yes. The main thing, as I was told by my practitioner friends, is that these values like W's or M's are very small. It's like 2 and 3 or something like this in real life because people don't want to pay for more gates. Okay. So what is the summary of the impact of ISW? It provided a very elegant model. It introduced a new technique from the multiplication of secrets encoded with amount of secret sharing. And it was based on the previous ideas from the MPC literature. So I think the take-home message from this part is that sometimes theory has an unexpected impact. Okay, so people were inventing MPCs for a different purpose, and it worked in this context. Also, that fundamental problems eventually find applications. So even if you, I mean, that's very common in theory that people invent some natural problem and they don't have a concrete application in mind yet, but it just looks natural. And sometimes it really turns out that it works in practice. But it's of course impossible to plan upfront. And sometimes what is useful is the general approach or the general spirit, not the technique itself. Okay, so that was the first part about the probing model. Can I take questions now, or are the questions planned at the end?
It's up to you, but we don't have questions in the chat right now, so maybe go on.
Okay, good.
Yeah.
Okay. I'm not monitoring the chat because it's like I'm looking at the slides. So if there are some questions, then ping me. Okay. Okay, so that was the probing model. And now I'm going to tell you about the noisy leakage model. And it starts with the following observation. So recall the criticism of the probing model that I mentioned before, namely that the real leakage looks more like this than probing. So it's like a noisy function, which raises a natural question if you can somehow model this noisy leakage. So maybe you could have a model that's more realistic, that instead of probing may assume that there is simply some noisy measurement of the device. There were several attempts to do it. Ian Chari et al. Crypto 99 had some model like this. In this talk, I will focus on the model of proof and revenge from Eurocrypt 13, which is, I think, the most common one now. So how does this model look like? The computation is again modeled as a circuit over some finite field, right? But the fundamental difference is that now we assume that every wire leaks. Okay, so there is the adversary, and he gets information from every wire. Okay, of course, he cannot get like full information about every wire because then there is no hope for security, but he will get like a partial information about each wire. Okay? So what is the information he gets? This information that is represented with this icon like this is simply modeled as something that's called delta noisy function, right? Denoted n, and I guess comes from noise. It's a function from the finite field to something. Okay? And the adversary learns all these values. Of course, it's a randomized function, right? So it's not like a mathematical deterministic function. It's a function that takes some input and outputs essentially some random variable. Okay, so what are these delta noisy functions? So they define it like this: that if you take a value on a wire and you have and you give it to the adversary, right? This is the value n, the adversary gets n of e. Then we say that n is a delta noisy function if leakages from random elements are close in the sense of statistical distance. Statistical distance is a very standard notion in cryptography. I don't have time to define it, but there is some kind of like a distance that measures how far are random variables from each other. Okay? And they just say that delta function is delta noisy if when you take two random elements, then their leakage is close, okay, in terms of this distance. Okay, so it looks quite different than a probing model. If you look at noisy model versus probing model, the noisy model looks like this, right? Everything leaks, and the probing model looks like this. Main difference is that in case of the noisy model, every wire leaks. In case of probing model, only small number of wires leak. And there are some similarities, though, namely that every wire leaks independently. Okay, so for example, in this model, we don't have anything like that. For example, the sum of wires can leak, or Hamming weight of the wires can leak, something like this. Okay? So every wire leaks independently. So this is a similarity, but there's this big difference that well, it's here some wires don't leak at all, and here every wire leaks. Okay, but since there are some similarities and differences, maybe we could try to reason about models and compare them. Maybe we could formalize somehow these relationships of being similar or being different, being stronger, being weaker. So this this brings us to the next part, which is the reductions between models. And that's where I'm going to talk about my paper with Alexandre and Sebastian from a few years ago. So basically what we observe, well, I mean, the first initial kind of simple observation is that sometimes one can show that one model is weaker than another model. Okay, so or it's not weaker. Like A is not weaker than the model B, or it's stronger or equivalent to model B, okay, which we'll denote like this for the purpose of this talk. Okay? So more precisely, what I will mean by model being stronger or not weaker than another is that for every crypto scheme X, if X is secure in model A, then this implies that X is secure in model B. Okay, usually it comes from for certain choice of parameters. Okay, like the threshold or the number of bits you can probe or something like this. Okay? So this is always a little bit tricky, and I always get a little bit confused myself. What means stronger? What means weaker? For me, because it could be defined in two ways actually. But for me, stronger means that for the purpose of this talk, it means a model is stronger than another one, or not weaker than another one, if from security of a scheme in this model, you get automatically security in the other model. Okay? So for example, the more you can probe your circuit, obviously the stronger model you get. Right, and ideally we would like to get security under strong and realistic assumptions. Okay, so let's now go back to noisy leakage versus probing leakage. So basically, our result that I mentioned before with Sebastian and Alexandre is can be summarized as follows. We show that epsilon random probing model is at least as strong as delta noisy model. Epsilon random probing I'm going to define on the next slide. So we introduce a new model it's a variant of probing model, and we show that it's at least as strong as the delta noisy model for delta equal to this. So this is epsilon divided by the size of the field, which is maybe not so great for larger fields, but if the field is just binary, then it's just 2 here, right? So it's not so bad. So more precisely, what we show that there is this model called epsilon random probing, and such that if we show that a scheme is secure in this epsilon random probing, then it is automatically secure in this delta noisy model of proof and reveal. Okay. So what is the epsilon random probing model? It's quite simple. It's very similar to probing. It's essentially probing, but we assume that every wire leaks with probability epsilon. Okay, so in probing of ISW, we had the model where the adversary could choose some number of wires and they were leaking. Here he doesn't choose these wires. He just gets some wires at random, okay, with probability epsilon. Of course, on average, this means that he should get around epsilon times n wires. Okay? When n is the total number of wires. And so this is the epsilon random probing, and again, the remaining wires are completely hidden. What is easy to see is that W probing model is at least as strong as epsilon random probing model for W equal to epsilon times n and with high probability, W equal to around epsilon times n. Okay, so basically, in this model, the adversary gets epsilon fraction of wires chosen randomly. In this model, he gets epsilon fraction of wires that he can choose himself. Okay? Of course, it's all probabilistic, so that's why I'm saying with high probability, and that's why I'm saying like approximate. Okay? But essentially, you can, if you have enough probes, you can emulate this epsilon random probing model in the standard probing model. Yeah. And what our reduction shows is that this is stronger, or at least as strong as the delta noisy model. Okay? So this is the main contribution of our paper, which by transitivity of this relation means that whatever is secure in W probing model is secure in the delta noisy model. Okay? So this model that looked a little bit like maybe not realistic, actually is quite realistic, because whatever you prove that it's secure in this model, you get automatically that it will be secure in a more kind of real life model, which is the delta noisy model of proof and reveal. Okay, so how to show it? Again, I don't have time to show it, and I even didn't define precisely what noisy leakage means. But basically what we do is we start with the following. We say, okay, we represent this epsilon random probing as epsilon identity function, where epsilon identity function is simply a function that works like this. This is a function phi that takes some input C, which is a field element, and outputs either C or bottom. So it outputs C with probability epsilon and bottom with probability 1 minus epsilon. Okay, so it's like an identity with probability epsilon, and it's a function that forgets totally its input on with probability 1 minus epsilon. Okay, so this is like a kind of like a trivial definition, nothing really deep here, but okay, it turns out to be useful on the next slide, because then we can say, okay, we can say that there's a way to define epsilon random probing such that every wire actually will leak to the adversary. It's just that what will leak is this function phi of C, right? So this is this function that mostly forgets its input, right? So we can say that it also leaks completely to the adversary. It's just that most of the cases it's meaningless what you get. Okay, so you get function phi of the circuit, and this function phi is now applied to every wire. It's just most cases it doesn't make any information. Okay? And now it finally starts to look similar to the noisy leakage, because now we can say, okay, it's applied to every wire. Okay? And what remains to show is that somehow n can be emulated or can be computed using phi. Okay, so that this leakage here can be simulated by this leakage. This leakage here can be simulated by this leakage here, just by looking at the outputs. So the main trick of the reduction is we take a delta noisy function n, and we come up with the function n prime, such that the following two experiments yield the same distribution for every input. So the first experiment is simple. You just take input C and you produce the noise out of it. And experiment 2 is you take wire C, and with probability epsilon you get C1 minus epsilon, you get bottom, and then you feed the Z to N prime, and then you get some Y. And then you say, okay, these two distributions should be identical. So you kind of simulate this leakage by leakage, which first actually gets either full information about the input or zero information, and then put something on top of it. Okay? And we do it by exploiting the standard properties of statistical distance. There's no time to show it now, but it's not really anything that's like very surprising. There, once you have this observation that you can use certain standard properties of statistical distance. So what are the consequences of this? There are some immediate improvements to the parameters of the original paper of Proof and Revert. There were also papers doing practical analysis of this. And turns out that this probing model actually, this random probing model is actually has some advantages over the standard probing model. Namely, allows simpler refreshing of secrets. We have a paper with my student Karol and Sebastian Faust at Asia Crypt last year on this. And in general, it's the consequence was that now there's a very good reason to study probing model or random probing model, and many papers now in practice are actually mentioning this because this gives them a justification. Okay, you have this noisy model, it looks kind of complicated, so let's prove security in the standard in the random probing model, and you get the security in the noisy probing model immediately. Even now at Crypto this year, there's a paper on this. Okay, so that was about leaking from circuits. Now I have the last part about bounded and split state models. So let me continue this. Okay, so all this starts a long time ago in the area called information theoretic cryptography. There was this very interesting topic called bounded storage model. It was introduced by Uli Maurer in the 90s, early 90s. And that was like completely different, again, completely different settings than anything that has to do with secure hardware. So namely, the setting was like this. Okay, so basically the motivation here is that you want to do information theoretic crypto, right? So you don't want to do anything like rely on any computational assumptions. You just want to do something that's information theoretically secure, like like quantum crypto, but in a different way. Okay, so so the model of Maurer was like this. Suppose there is a globe, right, and there is a satellite, and the satellite broadcasts to the whole continent, say, a very large stream of bits, very high bandwidth. And it's so large that no adversary can store it all in his memory. Okay, so there's adversary that can compute arbitrary function. So there are no computational assumptions here, except that the output of this function has to be small. So this is what I mean by bounded output. Bounded output simply means that the output of a function is much smaller than its input. Okay, if you just look at the length of the inputs in terms of bits, and yeah, so it's like half or less, something like this. Okay? So that was a very nice model. There were many papers on this. I was also publishing on this, and yeah, people were showing that you can do information theoretical crypto using such assumption. Okay, so you can have users here. They don't need to read this whole R. They just need to read small parts of R, and they can do lots of interesting things like encryption, authentication, even more advanced crypto protocols using this assumption. Okay, so that was like a nice theoretical topic. Nobody really thought about using it in practice. But there was a very nice key technique in this area. It actually took people some time to understand that that's the way it should be presented. So first you observe that you look at the distribution of the string R. So you assume the string R is completely random, right? So you look at the distribution of the string R given what the adversary learned, what he stored in his memory, and you observe that the entropy has to be large. Actually, what they use here is something like conditional mean entropy, not really Shannon entropy, but if you are not used to conditional mean entropy, you think of it as Shannon entropy. Okay, so there's like large entropy in R, even given what the adversary learned. Okay, and then you use an area called randomness extractors. These are tools also like very deep theory, lots of theory papers on this that allow to extract almost uniform randomness from a source that has high mean entropy, but is not uniform. Okay, so basically randomness extractors do something like this. You take high mean entropy source and you kind of squeeze it to something shorter that that is uniform or almost uniform. Okay? So that is like a very nice topic, and that was used in this area. Yeah, the area was also strongly relying on randomness extractors. Okay, and then there was another model that was called bounded-retrieval model. It was proposed by in two papers at TCC 2000. Sorry, it should be 2006 here. Times go fast. 2006. Yes. And the idea was to use similar tools to protect against virus attacks on computers. Okay, so what are the virus attacks? You have like a computer and you have maybe a virus on it that can steal all your cryptographic keys. So let's do like this, that we take, we assume that the cryptographic key that is stored on the device is huge, like say 100 gigabytes, okay? And so that no virus that hacks your computer can download it completely. So more precisely, you assume that the virus can compute arbitrary function of the secret that is bounded output. Okay, so instead of, so he cannot download all 100 gigabytes, but he can download 50 gigabytes, and we are even so generous for him that we allow him to do arbitrary computation before he decides what to download. Okay? So then the adversary, so the owner of the virus, the creator of the virus, learns just this bounded output function of the secret. And what was nice about this area was that actually it turned out that the same tools that were used in the bounded retrieval model, and sorry, in the bounded storage model, can be used also here. Although the context is of course completely different. So it's not nothing to do with like satellites and information theoretic encryption, yet you can use the same mathematical tools, and in particular extractors and all these facts about entropy in this area to construct schemes that are secure against virus attacks, assuming that you are willing to devote large disk space for the secrets. Okay. So that was the bounded retrieval model. And then there came another idea, and this is why I'm talking about this today, which is, okay, so why don't we use it to model leakage? Okay, so, and that's called lambda bounded leakage model. So now we have, we don't have any more like huge key. We have normal key, or maybe slightly larger than normal. And we assume that what can leak is some function which is bounded output, okay? So this will be again the bounded output function f, and everything will get scaled down, but we'll still have the situation that the mean entropy of function r, given what leaked to the adversary, is substantial, okay? So this f is again bounded output, okay? And that was a very nice area. Many people were publishing papers on this. There was some confusion at some time among practitioners because people were talking about bounded retrieval model and bounded leakage model at the same time, and then some practitioners actually understood that we want to put like hundreds of gigabytes on a smart card, which was not really what anybody wanted to do. This was probably partially our fault that we were not clear in explaining exactly the differences. But anyway, there was this moment when there were like lots of papers on this topic and top theory conferences. Yes, this is like I just had a space to like list the authors. Probably I hope I didn't forget about anybody important. yeah, you can see this very nice survey of Kalai and Raisin from 1 year ago, which surveys all these things. Okay, and that was to a large extent, this research was about public key crypto in this model. Okay, so again, what was the path of the research here? We have bounded storage model, like completely unrelated to leakage, bounded retrieval model, and then a bounded leakage model. Again, like different contexts, similar techniques. And this is, as I said, common in theoretical research. Okay, so how does probing compare to bounded leakage? It's easy to see that lambda bounded leakage model is stronger than lambda probing model, okay? Because lambda bounded function f can easily just retrieve lambda bits. Okay, so note that we don't have this inequality in a different direction, because of course, if you can compute arbitrary functions, you can leak much more than individual bits. So does it model leakage? Well, again, it doesn't look like this, right? Because you can say, okay, this looks like there are much more bits than lambda for any reasonable lambda. But then you can ask, I mean, what does it mean that there are some bits on the graph, right? So maybe you can compress it somehow. So effectively, you can say, okay, what really matters is not like how many bits there are in leakage, because leakage is noisy, but how many bits of information really about the secret key or secret that is on the device is carried in the graph. And then there was a generalization of this model called lambda bounded case split state model, which is a weakening of this model. And here we assume that leakage, that the key is split in several parts, okay, S1 up to Sk, and these parts leak independently, okay, so they are stored on different chips. Here I put like quotation marks because it's again, like, I think the way we think about it is more like a metaphor. I mean, we are like not experts in hardware, we don't know really much about how these things are implemented, but we say, okay, this is our metaphor in our theory papers, that you could like split it into different devices. Okay, I will get back to it on the next slide. Okay, so every secret is stored on a different device, say, and then you have bounded out the function f from each of these devices independently, such that the total length is almost lambda, right? So like one case split state model would be original bounded model, okay? Bounded output model. And it's easy to see that this model is still rather strong. So of course it's weaker than the lambda bounded leakage, but it's still stronger than probing, right? Because we don't, I mean, individual bits can still easily leak this way. Okay. So that was like a case split state model. And then pretty early, we had construction of a scheme in this model. That was a paper by Krzysztof Pietrzak and me on Fox more than 10 years ago. And this was a construction of a stream cipher where you start with some initial key. And the main feature of the stream cipher was that it remains secure even if the total leakage over time from the secret key is larger than secret key itself. That was achieved thanks to key evolution. It's also called rekeying in some other literature. So what is key evolution? The time is again divided into rounds and the key gets refreshed. Okay, so you have input and something leaks in round 0, that you get some output, then you get refreshing of the key, then you have next round and refreshing output and so on. Okay, so that's why whatever leaked earlier, it's kind of doesn't help because this gets refreshed. And the key point of our refreshing was that it was deterministic, so there was no external randomness and it was leaky. Okay, so you could also assume that it leaks. So what was our construction? I don't have much time to explain the details, but it was basically based on the idea of splitting the secret into 2 parts stored on different memory parts. So L and R. So you had the secret state S0, L0 that would be decomposed as L0, M0, and R0. And then you had the gadget. I'll tell you in a moment what this gadget is. This part remains unchanged. And then this one becomes an output. And then you are kind of like alternate, right? Then you look at this M. That was the previous output. You take L and you apply the gadget. Then R becomes unchanged and so on. Okay, so it alternates. Yeah, and that this gadget was constructed using pseudo-randomness using randomness extractors and pseudo-random generators. That was like a complicated, rather theoretical construction. For the details, you can see the paper. Yeah, that was the first paper on leakage at a very theoretical conference. In retrospect, we did one smart thing in this paper. Namely, we gave a title leakage resilient cryptography. Actually, I think the submission was leakage resilient symmetric cryptography, but I think then one of the reviewers actually advised us to remove symmetric. Okay, so actually at the time we were Googling if this title is not taken, and it was not. So it was like a very nice title. It sounds like there's more there in this paper than there really is, right? Because leakage resilient cryptography would sound like there's a whole cryptography constructed there, and we just constructed a stream cipher. And then we did also one stupid thing, namely we said it's secure in the only computation leaks model, which is a very nice model by Mikali and Raisin, but we should have solved it a little bit differently, because it is secure in the split state leakage model. Okay, so split state leakage model, meaning that what we're basically saying that if these values are unchanged, they are not leaking. While in fact, the same proof and everything works even if these parts are leaking. Okay? So, but we simply didn't think about that it's so important at that time, and that was actually the reason why some people really didn't like this paper in the practical community at the beginning, because they were saying that it's not true that only computation leaks. Okay? I think at that time we kind of made a mistake that we didn't talk to anybody from the practical community before publishing this paper. I will actually get back to this as one of my advices later. Okay, so where did this lead? There was a lot of work, especially by Yu or François-Xavier Standard, about making this practical or having new ideas that were partly taking ideas from this paper. Krzysztof then had a paper which called leakage resilient mode of operation, because this is kind of like a mode of operation. You can think of it like this. There is even a paper at this conference, at CHESS 2020, that cites this paper of Krzysztof and mine, and also cited in the context of mode of operation. There is a very nice talk by François-Xavier on Eurocrypt that talks more about such things. I mean, partly the talk is not only about this, but there are some slides on this. And there were lots of interesting theory results. Also, one of the tools that we used there was computational pseudo-entropy, which is a nice theoretical concept. So there were people writing papers on this. Okay, and the last thing I wanted to tell you about is the inner product masking. This brings me back to the extractors. So as I told you, randomness extractors are very useful in this area. And here is an application that I had with Francesco Davi and Daniele Venturi 10 years ago, which kind of like a simple observation. You have suppose you have two functions f and g that are bounded output, so their outputs are shorter than their inputs. You have a finite field, and you have two vectors of length n over these fields. Then if you put these two vectors on a device, two devices, and these both devices leak, then the adversary gets almost no information about the inner product of these two values. Okay? By inner product, I mean something like this. Okay? Sorry, this I should go to the subscript. So what it basically means is that I can kind of secret share a value on two devices in such a way that even if they are both leaky, the adversary will not learn this value. Okay, this inner product defined in a standard way. This simplest way to think about this is over Z2, because then this inner product is just like you look at how many positions there are that are equal to 1 on both vectors, and you check if they are the number is even or odd. Okay, so this is like standard thing from a randomness extractor. The fact that this inner product is secured, and I mean stated in a slightly different way in this literature, but basically that's what they show. And this was like from the 80s, or that Chor and Goldreich paper showing that that this is an extractor. Okay? So this is in such a situation the adversary gets almost no information about the inner product. Okay? And this led to something which is called inner product masking. So we can have, again, masking is a different word for encoding. So you define encode and decode as follows. So to encode the value, you produce two vectors, L1 and R1 Rn, such that their inner product is S. To decode, you just compute the inner product. And then you can store these two values on different chips, or you can even store them on a single chip, because we have this fact that split state model is stronger than probing model, right? So if it's secure as even in the split state model, then it's also secure in the probing model. And a nice thing about inner product is that it is linear, right? So if you fix one of this LNR, it's linear with respect to another one. And this can be exploited to build some new things, like construct more complicated constructions, not only storing values, but also computing on them. There were also some papers by more practice-oriented people who are studying this technique. Okay, so this is called inner product masking. Okay, so that was more or less everything I wanted to tell you about research. Let me just finish with some conclusions. I think about future work, I think, well, if you want like a concrete problem, then I think better constructions in the random probing model is a nice problem, because this implies security in the noisy leakage noisy leakage model. Then there is one big area which is security beyond leakage attacks. So one big area that I haven't had time to mention is tampering attacks, where the adversary not only leaks the information from the device, but also tries to tamper with this. We have this tool called non-malleable codes there. Maybe you can do something like general compilers also that would be secure against tampering. There is a paper called Private Circuits 2 by the same authors as Private Circuits 1 as W plus Major Prabhakan. And yeah, it seems that there is larger distance between theory and practice than in leakage, in tampering. And finally, I think one area that's actually I think maybe interesting is, although it may sound a little bit like we are too much following like the latest fashion, to look at the interaction with the blockchain, because so there are some specific things about the blockchain that make it interesting. In particular, what I mean is studying something called hardware wallets, cryptocurrency wallets. So wallets are devices where people actually store their coins, or devices more generally speaking that are used to interact with the blockchain. And blockchain users are especially tech savvy, right? So they are people who could be early adopters for more complicated solutions. And they actually also want to have things, or in the future they will want to have things that are more complicated than just authentication and encryption. They will want to have devices that want to execute protocols because of all these cryptocurrency protocols based on smart contracts. You can also exploit somehow smart contracts for security. So if you have a device that interacts with a smart contract, maybe you can use some features of a smart contract to enhance the security. Okay, so I think this can be actually an interesting area. A final remark I wanted to give is that there is this different research studies between theory and practice. So theoreticians really care that the results should be elegant, even the cost of practicality. We care a lot about like equivalence, impossibility, proofs are very important. Practitioners are more focused on real life problems, and they really want to have real life solutions that reflect with the assumption that reflect the reality and real efficiency. So usually practical papers have some graphs about some simulations or things like this. So the consequence is that the papers, research papers in these two sub areas of computer science have kind of different look and feel. So I sometimes have trouble reading practical papers, and I guess it's also the other way around. Because simply, for example, different things are stressed in the introduction than in these two different areas. So I think it's very good to talk to each other. And I really appreciated talking to many of my practitioner friends, especially Francois Xavier Standet. Okay, so that was it. Let me thank you for your attention, and also I'd like to thank all my co-authors of my leakage papers. especially Sebastian and François Xavier, who also helped me with this presentation. Thank you very much.
So thank you, Stefan. So I think we will now be taking questions. So please write your questions in Zulip chat if possible, and I will read them. Or if you want more interactions, it's okay to unmute.
Do I see them somehow? Wait, I'm not.
Yeah, if you're, they should show up at some point. But anyway, so to kickstart, I will maybe ask the first one. So very often, so as you mentioned, so now in masking papers, we often use the argument that says that since the probing, so we do proofs in the probing model and then say that based on your reduction, this proves security in the noisy leakage model, and therefore so it's reasonable to say that the proofs are meaningful in practice. But so from what I understand, so the reduction is not so tight, and so actually you would need maybe a masking order which is linear in the size of the circuit to really argue security, right? Which
Well,
we never have in practice.
The reductions, I think, is kind of tight actually. So it's in general a problem with the model. I mean, like, I think because basically what tight, what would it mean that is tight or not tight? We have a reduction that shows a reduction in one direction, right? That's what I had on my slides, and I'm now scrolling back to find it. Yes. Yes, that was the reduction that we had, right? And now the question is if you can get inequality in the other direction, right? So if you can get something like, right? So if you get both for the same delta and epsilon, that would mean that the reduction is completely tight, right? So if you go back and forth, you would arrive with the same epsilon, right? And I think if you use this, I think there is actually an example that shows that this reduction is tight up to factor 2 or something like this. So you would like go back and forth, you just lose factor of 2. This, as far as I remember, it's like this. So it is tight, but the problem is that then you, of course, I mean, the delta noisy model is rather I mean, maybe simply delta noisy model is still too strong to get like better parameters, right? Because of course, I think what you are aiming at is the problem that we have is that, for example, if you have like a constant fraction of bits leaking, then even ISW is not secure, right? Because you get things like, I mean, against constant fraction leakage, right? Because if you leak a constant fraction of wires from like this square that you have in ISW, then you leak your secret. So I guess I think it's simply a question about like improving finding a better model than the noisy leakage model, more realistic, that would still allow proofs. So if this answers your question. I mean, yes. then we had a follow-up paper that introduced average probing model. That was some time ago, so I don't remember. There was a different model that allowed a little bit better proofs. Maybe we can take it offline because I don't remember now exactly the details.
I see. Okay, thank you very much. So yeah, so but so then so if I go back to my argument, so we often say, so to justify that masking is a good countermeasure, we will say, okay, this proves security in the noisy leakage model, but the parameters we use don't actually apply. So would you say that so it's still reasonable to say something like this, or we are actually we are cheating in some sense? I
sorry,
mean,
yes. Can you maybe repeat the question? I'm not sure if I understood.
yeah. So people use masking with a fixed order in practice, right?
Yes,
Maybe
yes,
order
yes,
3
yes,
or something.
yes, exactly, yes.
Which probably does not prove a high level of security that is reasonable with respect to real world attackers.
Yes, it's also kind of like wishful thinking to a large extent, right? Because you have this problem, of course, that, for example, even the reduction between like random probing and standard probing assumes something like Chernow bounds at some point, right? Because you need to, I mean, like, could it be that maybe, you know, you have random probing with probability 10% of leakage, but just for a small number of probes, you can still get like leakage from all. I mean, right, a good chance, right? So I think we are not there yet, and we are kind of, you know, we have some model that makes some sense, but how realistic this really is, it's a good question. I mean, you know, I had this the kind of like theoretical approach that basically says, I mean, the approach is whatever comes from practitioners, it's for sure practical. So I'm kind of don't feel responsible for like the part, like if noisy model, to which extent the noisy model is realistic or not. Yeah, I guess it's still like, you know, a little bit of wishful thinking, but I think also the situation is like this, of course, that since this is in general kind of like a little bit hopeless area, then like, you know, if your hardware leaks, what to do then whatever, whenever you have some theoretical reasons to use something, then not something else, then it's already good. No?
Yeah.
That
Okay.
would be my guess.
Thank you very much.
We can take it also offline.
Any other questions from the audience? Oh, so in the chat, Amir asks, any idea how we should close or at least shrink the gap between theory and practice? In particular, I mean, which kind of practice-oriented information you need in your research or to build a model closer to reality. So
yeah, so as I said, maybe I'll show on my last slide. So this wait, something disappeared now. So basically, I think one thing that would be interesting would be to look at this tampering attacks. Okay, so tampering attacks where the adversary can also influence the hardware. And so we have this tool called non-malleable codes, and there are many papers on this, and I should be happy because that's like I was on the paper that proposed this notion, so I'm getting citations. But still, I think this is an area where people have lots of nice theoretical ideas, but don't try to confront them with practice. Okay, so people come up with new non-malleable codes can come in different flavors, and you have a new model for non-malleable codes. You have a nice theory paper, and you never talk to practitioners to ask them does really correspond to anything that you experience in real life. Okay? So I think that would be a very nice topic, actually, that, I mean, at some point we could sit and try to explain what we do in non-malleable codes and try to kind of find out if there are any useful things for the practical community there.
Yeah, I suppose so. Like, so it seems that so say, for example, private circuits 2 didn't have nearly as much impact or as much relationship with the practice community
Yes.
as the original ISW paper.
Yes. Well, and another even more extreme type of attacks are hardware trojans, right? I had I mean, I was trying to work on this, and I'm still trying. And this looks like a very complicated area. It's, I mean, of course, you can come up with some theory solutions, but to understand what can really be done against like malicious hardware manufacturers, I think there are not that many papers on this, but not because it's not an interesting or relevant topic. It's just because nobody has really that many great ideas how to approach it. Yeah. So you know, all the settings where even the manufacturer of your hardware is malicious. What can happen
That's
then?
interesting. Thank you. So in the chat, Mathieu Rivin asks, thanks for the excellent overview. Regarding the random pruning model, how much do you think new constructions could get close to 1 for epsilon, which would translate to achieving security with small noise in the noisy model?
Well, so we were trying, so I think the multiplication is the hardest part, right? I know that some good people were trying to think about it. I was not trying to think much about this, but measuring or basing on how much people whom good people whom I know thought about this is not like an immediate thing. I mean, it's a nice open problem, but it's I think we'll get there, but I mean, probably it will be again like, you know, we get initially some very theoretical results with some, you know, asymptotic nice complexity, but not relevant to like probing like 3 wires or something like this. But I think we'll get there. Just that it's kind of like I thought a little bit about this and I couldn't find anything, but I was not the only one, and some people thought more.
Thank you. Anything else from the audience? So if not, we're actually a bit over time already. So I suggest that we close this session, and everyone can meet in the in the social gathering afterwards, where hopefully we can talk offline.
Thank you very much.
So thank you very much again, Stefan.